Welcome to Lecture 6 for ECE 203. Today we're going to talk about harmonics and periodicity. So to begin, let's talk about harmonics and just have in mind this simple signal x of t equals cosine of 2 pi f naught t, where f naught is just what we'll call the fundamental frequency. So we would say that frequencies that are integer multiples of this fundamental frequency, so in particular 2 times f naught, 3 times f naught, 4 times f naught, and so on, those are the harmonics of the frequency f naught. And we would say the signals, cosine 2 pi times 2 f naught t, and then a cosine with frequency 3 f naught, cosine with frequency 4 f naught, those are the harmonics of the signal x of t. So it's a relatively simple idea, and all it means is that there is components of the signal that are integer multiples of some fundamental frequency f naught. So one way to visualize this and kind of see where this comes from is to think of a piano chord or guitar strings. And if you took a guitar string, right, and pinned down both ends, which we see, which is actually the case in the guitar, right? So there's that end is tied down, and that end is tied down. And you were to pluck the guitar string, you actually see that you'd set up some vibrations on the string, and those vibrations on the strings, those are waves, right? But they have this constraint that the half wavelengths have to be integer multiples of that total length, okay? And that's relatively easy to visualize. In this drawing, we can see this first one, this would be the fundamental frequency f naught, and then at this one would be some frequency 2 times f naught, and this third one, of course, 3 times f naught, and so on. So these would be all the harmonics of the fundamental frequency f naught. This last one might be 7 times f naught. Right. So harmonics are a pretty straightforward idea, and more generally, we just see the spectrum of a signal. If it has some fundamental component at a frequency f naught, and if we see that there's energy at 2 times f naught, 3 times f naught, 4 times f naught, we say those are the harmonics of the signal. So to see a few examples of that, let's take a look at middle C of a piano. So if we, this is an actual recording of middle C played on a piano, and if you look at the time domain signal, as expected, it kind of ramps up very quickly. So it's from silence, then a loud noise when the key is struck, and then it decays off after about 2.5 seconds. It's a little more interesting if we look at the spectrum of the signal, right? If we look at the frequency content of the signal, and that's the lower plot shown here. And we can see there are indeed harmonics, and that of course is just visualized by these components that appear to be at integer frequencies of each other. Okay, there's fundamental, there's the first harmonic, the second harmonic, and so on. The third harmonic. Okay, and middle C in piano is actually a note that's at 261 hertz. And it does have a large number of harmonics. You can see here maybe it's 10 harmonics, maybe there's a few more. Okay? So we'll see this in a second. I'll show you guys the actual MATLAB demo, and we can listen to the middle C and see the different harmonics up close using MATLAB. The next thing I want to point out is we talked about the time domain and the spectrum of my voice saying the word hello in last lecture. I just wanted to bring that up again and show you guys that if we zoom in, okay, and that's this bottom plot here, if we zoom in on the spectrum, it's pretty easy to see my voice has a number of harmonics. Okay, so we might say that there appear to be there appears to be a lot of energy at about 141 hertz, and then integer multiples of 141 hertz. So this harmonic would be at 282 hertz, and so on. Okay. This one would be 3 times 141 hertz. What's interesting about this is not only do we see that the piano or a guitar string creates harmonics, but the human vocal cord also creates a number of harmonics, which is particularly interesting. And this is useful from a mathematical perspective also for a number of reasons. We'll show, not today, but in the next 2 lectures, that any periodic signal can be represented by a sum of sinusoids that are harmonically related. This will be something called the Fourier series. So we'll spend quite a bit of time looking at signals that have harmonically related frequencies. So let's actually look at how this example of the piano noise and my voice hello work in MATLAB. So what I have here is just this simple code that's taking the wave file called piano.c.wave. It's just a recording of the middle C played by a piano. It's loading it in. It's going to plot it in time domain, in the time domain, and then it's going to plot the spectrum of the signal. Okay, so let me just run that really quick, and we can hear the middle C of the piano. Turn up volume slightly. What you want to note in the spectrum again is now I can see if I zoom in that middle C, that first fundamental frequency should be at about 261 hertz. Okay, and then at integer multiples of 261 hertz I actually have the harmonic component. So it's made up of some number of harmonics. If I zoom out, you can see there's a fair number of harmonics. Okay, so what I'm also doing in this code is then I'm doing the same thing we did before with the hello voice in the previous lecture, and that's just taking the largest 10 sinusoidal components and seeing how the signal sounds if we only include those 10 sinusoids. So that's what I'll play next. Okay, it sounds a little bit like middle C, but you can see from the spectral plot we lost a lot of the harmonics. So it sounds a lot more like kind of just this single tone, right? So not as pleasant of a sound. Let's go back here, and now instead let's say we'll include 100 tones. So let me run this again. First, the original, the middle C of the piano will play. It's a nice, clean, pleasant sound with a number of harmonics. Okay? Now when we continue, again with 100 sinusoids, piano middle C sounds relatively close to the original C. So it sounds pretty good. We'd have to include a fair number more sinusoids for somebody that was at a critical ear to not be able to distinguish the two. In particular, there's a bit of a ringing sound at the end. But again, if I zoom in here, I can see I pick up most of the harmonics. Most of the harmonics are picked up. Again, if we were to say let's include some large number of sinusoids, say 2,000. We run this again. The original sounds nice and clean. Again, the signal now with only the largest 2,000 sinusoid sounds almost identical. So lastly, I want to show you guys the hello, my voice saying hello, and look at the harmonics of this signal. So let me run that quickly. Hello. All right. So now if I zoom in on this spectrum of this recorded hello, me saying hello, we'll see that indeed the human vocal cords, even with me saying hello, creates about 3 harmonics here, right? So the first chunk of energy in me saying hello is somewhere around 141 hertz, and then there should be another peak somewhere around 280. Okay? And sure enough there is, and then a third one at 3 times 140, so somewhere around 420. So surprisingly enough, there is, even with the human vocal cords, a number of harmonics show up in the signal. So for the rest of this lecture, I want to talk about precisely what it means for a signal to be periodic. So from a mathematical perspective, we say a signal is periodic with period t naught if we can write the signal x of t as being equal to another signal, or the same signal, evaluated at t plus t naught. So that's this statement here. And that has to hold not just for one t, but for all t. So a simple example of that is just a sinusoidal signal. Okay. So again, we have x of t equals cosine 2 pi f naught t plus phi. So say f naught is the frequency of the sinusoid, right? And the period, of course, equals 1 over f naught. And we want to check now, can we write x of t equal to x of t plus t naught for some t naught? That's the question. And if we can, that signal is periodic and it has period t0. So how do we go about doing that? Well, the first thing we do is we just actually write out exactly what we have above. And that's x of t, which is cosine 2 pi f naught t plus phi. We would check, is that indeed equal to cosine 2 pi f naught, now parentheses t plus t naught, right? We just replaced t with t plus t naught plus phi. If we can show that this is true for some t naught, for all t, then we'll be done. Okay, so let me just continue this here, and you can write this right-hand side. So this is what we want to check. Okay, we want to check this line, and if it is true, then the signal is periodic. We want to figure out what t naught is. So of course, if we just write this again is, now I'm going to plug in t naught equals 1 over f naught, and I'm also going to expand out this product. And we get cosine 2 pi f naught t plus 2 times pi times f naught times t naught, right? Let's just write that as 1 over f naught. Right? T naught equals 1 over f naught plus phi. And of course, right away what you should see is that these guys cancel, the f naught cancels, and we're just left with an additive 2 pi. Okay? And so that additive 2 pi, right, remember, cosine of any number is the same as cosine of that number plus 2 pi, so we can just get rid of that 2 pi, and that of course is equal to cosine 2 pi f naught t plus phi. Alright, so we're done, and relatively easily we verified that cosine is periodic with period 1 over f naught. Simple thing most of us already knew, but we just wanted to write that out and make sure we could walk through the steps. So another example is a harmonic signal. So let's imagine we can write a harmonic signal as the sum of a number of sinusoids, okay? And each one of those sinusoids has a frequency that's an integer multiple of the fundamental frequency. So you see that written right here, right? And they all have maybe different amplitudes and maybe different phases, so a sub k and phi sub k. But the key here is we have k times f naught, right? And so just integer multiples of f naught. So again, we can do the exact same thing we did before and now just verify that we can replace x of t with x of t plus t naught. So that's what we did in this line. We set t equals t plus t naught. And then, of course, again, we just expand this out in the same way. And now what you see, exact same thing that we saw before. We have this f naught and the t cancel, and we're left with 2 times pi times k. And remember, k is an integer, and that's because we're looking at a harmonic signal. Then, of course, all of these components, then these 2 pi k, those are all, we can ignore all of those, and we can just essentially x out this whole term, right? And we're just left with the original signal. So indeed, harmonic signals are periodic. Let's see, if we're given a multi-component sinusoidal signal, okay, so a sinusoidal signal that's the sum of sinusoids at different frequencies, then how can we verify if it's periodic or not, and how do we find what its period is? Well, to do that, again, we would just look at the definition of periodicity. Okay, so we need to find the smallest t naught. Okay, and the smallest t naught, remember, that's going to be called the fundamental period. And once we found that smallest t naught, then we can just relate it to frequency. Okay, so how does that work? Let's look at a particular example. Let's look at the example x of t equals 3 cosine 2 pi t plus pi over 4. So that's a sinusoid at 1 hertz, right? And let's subtract cosine 5 pi t plus pi over 7, for example. So that, of course, is a sinusoid at 2.5 hertz, right? So the first one's a sinusoid at 1 hertz, and the second component is a sinusoid at 2.5 hertz. So the question is now what's the period of this combined sinusoid? Well, the period of the first component is, of course, 1 second, right? It's just 1 over 1 hertz. The period of the second component is just 1 over 2.5 hertz, which should be 0.4 seconds. So now our task is to find the smallest t naught such that that t naught is an integer multiple of these other frequencies. That's how we would proceed here. So precisely what do I mean by that? Well, just to see this example, if we set, so t1, right, if we multiply that by an integer, and that gives us a number, and then we can multiply t2 by another integer, and that gives us the same number, then that number is the period. Okay? So let's do that, just that. If we take t1, which is 1 second, and multiply it by 2, we get 2 seconds. So that just means if I were to plot this, if I look at 2 seconds, then that signal should have completed, this first part of the signal should have completed 2 complete cycles, right? I'll try and draw that. Okay. So you could also look at now what happens to the second component, because it also has to complete an integer number of cycles in that 2 seconds, otherwise it won't be periodic. So in fact it does, right? If we multiply t2, which is 0.04 seconds, t2 equals 0.04 times 5, that should give us 2 seconds. Okay. So let me maybe draw that signal. This is going to be a little harder because I have to make it complete 5 periods. So maybe I won't even, well, I'll give it a shot. So say 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. So we have these 2 signals, right? The first one in 2 seconds completes 2 periods. The second one in 5 seconds, or in 2 seconds, completes 5 periods. When we add these together, it should be relatively clear that since they both complete an integer number of periods in this amount of time, then we actually have that the sum of these 2 signals is periodic with period 2 seconds. All right? So just as a note, we could also do this and find the same property holds for a period t0 of say 4 seconds. But again, we're interested in finding the smallest t0. Right? So t0 corresponds to a frequency f0 of 0.5 hertz, and we would say that's the fundamental frequency of this sum of sinusoids. And again, just let me circle what's most important here. So we have a number of sinusoids added together, and we want to find their period, their fundamental period, their fundamental frequency, and we need to find the smallest t0 such that that t0 is an integer multiple of the periods of the individual components of the sine wave. All right. So it's helpful to do a few examples, and you guys you'll have to do a few in homework. And I think when you sit down and think about this isn't too tough. It's relatively straightforward. So the next thing I want to talk about is when signals are not periodic or aperiodic, so to speak, and that happens when there's not a t0. Okay, and so t0 has to be greater than 0. Can't say t0 equals 0, and then it would just be trivial. But when there is no t0 such that we can write x of t plus t0, and this is, again, I need to say for all t. Okay, when there's no t0 greater than 0, such that x of t equals x of t plus t0 for all t. Okay, relatively simple definition, but it does arise in multi-component sinusoidal signals. And an example of that is the signal x of t equals 3 cosine 2 pi t, right? So a frequency of 1 hertz, right, minus cosine of 5t. And what you'll notice here is that there's no pi in this expression. So the frequency of the second component is actually 5 divided by 2 pi, right? And pi is an irrational number. So no matter how hard we try to find a t0 that this signal satisfies this equation here, we won't succeed in doing it. And you can think about that if you draw a picture, that you'll never find an integer number of periods of the first term such that an integer number of periods of the second term also lines up. And another way to say that is that there are no two integers, m and n, such that m times the period of the first term, which is 1 second, is equal to n times the period of the second term. Okay? There's no integers that satisfy that for periods of 1 second and periods of 2 pi over 5 seconds. Okay? And it should be a clue anytime you see a sum of sinusoidal signals, a multi-component sinusoidal signal, where you have, say, a factor of pi in the frequency of 1, but not a factor of pi in the frequency of the other components. Then it should right away be able to say that the signal is indeed aperiodic or not periodic. So the last thing I want to mention in this lecture is how we can view finite duration signals and use all the tools we're going to develop for periodic signals, apply those to these finite duration signals. So what do I mean by finite duration signal? If I just take a signal that, say, starts at time equals 0, and it's always 0 before time 0, and then it stops after some time t, meaning the signal is 0 after some time t, then I can view this as a periodic signal. And the way I would do that is just kind of lining up back to back. That's the picture I have drawn here. copies of that particular signal, right? So another way to think about finite duration signal is just saying the signal is not defined outside of t. If t is less than 0, the signal is not defined, and if t is greater than capital T, some duration, then the signal is not defined. Okay? So, of course, I can just also line those up back to back, and then I get a signal of period t, right? If I just repeat that finite duration signal every capital T seconds back to back, then we have a periodic signal. And why this is important is we're going to develop tools for periodic signals, but in reality the signals we encounter in practice and the ones that we can store on a computer are they're of course finite duration. So treating them as periodic is very mathematically convenient.